All right, folks. Well, this time around, I want to take a look at kind of a variety of different issues that crop up with our intermediate representations, these representations that we're going to manipulate and change and try and capture different aspects of the program behavior for different purposes. So, fair range of different things that I want to talk about today. One of them is just in terms of modeling the control flow in a program. So what's the sequence of operations? When do we jump from one block of code to another, right, on a subroutine call, or when we hit an if-then-else, or when we hit a loop? So a variety of different things that we can look at here. And one possibility is to take the linear code idea that we were looking at last time around and combine that with a control flow graph. So we'll spend a little bit of time going over that as an idea. I want to spend some time looking at the choices we might make for how we name the internal variables that we look at. We touched on this briefly with the single static assignment idea, but we'll spend a little bit more time on that. I want to talk a little bit about the memory models that we're assuming in our internal representation. So whether we're kind of taking a register-focused approach or a memory-focused approach. And I want to come back and start talking more about symbol tables and how our use of symbol tables and our representation of symbol tables ties into whatever internal representation we're using here. So first off, with that flow of control side of things. So we want to go through and be able to model iterations, so loops, be able to model selections, so ifs and elses, be able to model subroutine calls and returns, be able to model go-tos if the language supports those. So a fairly wide variety of things that we want to be able to deal with. So what that means is that there's going to be kind of a block of sequential statements that you execute where there are no jumps around, there are no changes in the flow of control. And then you hit a point where you might or may not jump from the current instruction to someplace completely different in the instruction sequence. So we want to try and model those blocks of sequential statements and then jumps between them. So if we're taking a linear code approach, then we can say, well, let's treat the block as the suite of linear code statements that has, exactly one entry point and then a possible exit point. And so everything in there is a block where there's no possibility of jumping into the middle of it and no possibility of leaving it. That's a block. And then we'll just identify all of these different blocks and identify all of the different places that we can jump from the end of one block to the beginning of some other block. So our control flow graph is going to treat each of its nodes as one of these blocks and a directed edge from the end of one of the blocks, right, from one node to the start of another block, another node. So somehow we have to be able to construct that. So what we can do is to try and find all these entry and exit points. So we can go through and somehow there's going to have to, any place where you're jumping to a block of code, there's got to be some kind of a label there identifying, you can jump to this point. So what we'll do is make one pass through the code to find all of these possible entry points and to identify the first statement in each of those blocks. So essentially the first statement after every label that's in the code. So we'll call these statements the leaders. A block will end as soon as there's a potential jump or branch, but if we've got our leaders identified, we can go through and figure out our blocks just based on that. So what we'll do is make two passes. The first pass, we go through and identify all of the leaders. And then in the second pass, we'll go through all of our statements again. And each time we hit a leader, we're looking at statements saying, okay, this is in the leaders block, this is in the leaders block, this is in the leaders block. As soon as you hit another leader, that's your indication that you've left the previous block. So the previous statement is the last statement in the previous block. So this lets you go through in two passes, right, identify all the leaders, and then identify essentially all the statements that come right before a leader and end the previous block. So you go through and identify all of your blocks, and then you can go through and identify all of the potential transitions between them and start building your control flow graph. So another one of the issues that I wanted to deal with was the idea of choice of internal names. Right, we can as we're going through, and we talked about this idea of having sort of internal variables or temporary variables to hold the results of individual expressions, right? Subtrees, if you like, of the program that we've been translating. So when we're going through, we can either create, there's going to be places where we're going to create sort of brand new names for things that aren't clearly named in the original sources. But there are going to be places where we have a choice between using the same names as they used in the source or making up a new name, right? Creating a brand new variable to hold a particular value. So what we'll do is take the similar sort of approach as we did with the single static assignment, where let's assume at the beginning that we'll copy all of our variables into temp variables, right? We can safely reuse those as long as the values aren't changing. And what we'll do is stick with the naming convention that the source code originally contained. And then our second approach, we'll go through and pick new names for everything. That's essentially the idea. So if our original was this, where we're going through and saying, okay, W is X times Y, and then X is W plus Z, and Y is X minus Y. So we're reusing these things, right? We're updating the value in X, and then using it later. We're updating the value in Y, and then using it later. So we could go through, and again, here assuming that we're using a kind of register-like approach where we're copying our 4 initial variables into temps, but then basing the names of the variables on, or the names of our destinations on the names used in the original. So when they said, W is equal to X times Y, we'll use whichever register we were keeping W in. And when they say X is equal to W plus Z, our destination will be whichever one we had X in. So we're overwriting the value of X, we're overwriting the value of W, but doing it in the same fashion as they did in the original. So we know this is still going to have the same behavior as the original, and the code that we're using is pretty much matching the original code, and then at the end we copy everything back. So the alternative is, instead of sticking with the names they used for the results that we compute as we go along, we come up with new internal variables. So when I perform this multiplication, instead of sticking it back in T1, I'm going to leave T1 as it originally was and store the result in a new variable. And similarly, when I perform the addition, instead of overwriting the value that was in X, I'm going to store it in a new variable. And I'm going to use those new variables, not the original W's and X's and Y's and Z's, as we continue through this. Now what this does is it separates our code a little bit. It makes it a little bit more independent of the original source code. It might be that there are possibilities for rearranging some of these statements, doing some of these things in a different order now that we're using different names for these, that wasn't potentially visible in the original source code. It gives us some opportunities for optimization that we might not have spotted if we'd stuck with the original naming scheme. So it just gives us some possibilities to work with. All right. One of the other things I wanted to take a look at was how our internal representation thinks we're modeling memory. And the big distinction that we're going to draw here is whether we assume that we've got kind of a register-focused approach to things, or whether we assume that we've got a memory-focused approach to things. So we'll look at two different models. A register-to-register model assumes that as much as possible, we move data into registers, keep it there as long as possible, and write it back as late as humanly possible. A memory-to-memory model assumes that we leave things sitting in memory as much as possible, and at the last possible moment we move it to a register, a temporary register, use it, and then put it back in memory. So two very different kind of philosophies to how we'll structure this. So the register-to-register model for our little internal representation here just ignores whatever the number of physical registers that are actually going to exist in the target, and we're just going through and assuming that if it's possible, we'll dump things in a register. So we'll create virtual registers for almost everything, if you like, and move everything into those, leave them there as long as possible, and write stuff back at kind of at the end of whatever it is we're doing. And this kind of assumes that when it comes time to actually map our internal model to our target language, if there aren't actually that many physical registers available, then we'll come up with some kind of prioritization scheme that says, okay, well, the most used registers will actually wind up in physical registers, and the other ones will spill to memory, and when we actually need them, we'll bring them in, use them, and then put them back in memory. So it assumes that we'll keep everything in registers as much as we possibly can. And again, it's a simple approach. It can give us some good opportunities for optimization further down the road. The flip side is that we'll assume we leave things in memory as much as possible. So we'll assume values are kept in memory until we need them, move them to a temporary register just before we need them, and if the value there changes and we need to put it back, we copy it back. If we don't need to copy it back, we don't copy it back. But the idea here is that we'll use fewer registers, and sometimes the memory-to-memory model might be a better matchup with the style of operations that we've picked for our internal representation, right? Maybe the set of linear code operations that we decided to work with is more suitable with a memory-to-memory model or simpler with a memory-to-memory model. So there are a variety of different possibilities here, but those are the two big ones to focus on. All right, last topic I wanted to go through for this was the role of the symbol table with our internal representation. Right, we've been playing with symbol tables as we play with Lex and Yak and doing our parsing and doing our context-sensitive checking, and we've kind of assumed these things exist. You don't have to have symbol tables. The idea is it's often a convenient way to cross-reference between different parts of a program as you're working with it. If you see a place where a variable is used, then you don't have the declaration structure right at hand. You go and look up the information that was discovered earlier and stored in a symbol table. So we can either have kind of this notion of a symbol table with information about all of the different declared things, or we can go through and whenever we see a reference to something, we can go off and search through whatever our derivation structure is and look for where it was declared and find it and drag the information out from there. Right? That's an entirely valid and entirely plausible approach, but typically it's going to be a slower approach if we're constantly having to go back and search for where we declared these things and look up the relevant information, which might in turn involve looking up information about something else. So it is a pretty common idea to go through and build a symbol table to have the information about whatever's been defined and declared. Now, I will often refer to this as, the symbol table, but in point of fact, it's pretty common to have multiple different symbol tables for different purposes, right? A symbol table for your function definitions, a symbol table for your variable definitions, maybe a symbol table for your structure definitions, right? So there might be a variety of these things for different specific purposes. So all sorts of data that you might be storing in these things, right? Obviously, we've looked at some of these ideas with a variable. You might be storing its name, its scope, its data type, its storage type. Where does this thing exist? Its memory address if it's stored in memory. For functions, you're looking at the name, the return type, the types of parameters, the number of parameters. Right? For the labels, you might be looking at names and addresses and scoping. Maybe if you want to prevent jumping across scopes to labels. Right? For arrays, you might be considering the same sort of information as with variables, but you're also thinking about the array dimensions. If you're looking at things like structures or records, then you're looking at recording the different field names, the data types associated with them, and the sizes associated with them. And so there's all sorts of different kinds of information that you might be storing about different things in different symbol tables. Now, just like we looked at our syntax trees and our linear codes, this is something where we've got a bunch of information we want to store, and we want to be able to search and look up information effectively. So we might just be going through and saying, well, let's just have a record for each thing in whichever symbol table it is we're looking at right now and just have an array of these things and a counter of how many of them we've declared so far. So it's nice and simple, but of course if you're trying to search for something, you wind up with an order and search, or else you wind up trying to build somehow a sorted array so that you can do a binary search type of idea, but then you've got more complicated inserts. It might be the case that you're looking at something like a binary search tree instead, where again we come up with some idea of what an ordering looks like on the data that we're storing, and maybe a binary search tree based on the names of the functions or the variables or whatever it is we're storing. And so again, you've got a more complicated structure, but you can get log-in search time, just based on the tree height, assuming we're keeping a balanced tree somehow. Or again, we could look at a hash table kind of approach, where we come up with a decent hash function based on the names or names and parameters or whatever the values are for the kinds of things we're storing in our symbol table. And each hash table entry has a bucket with potentially a bunch of different records in it, and we just apply the hash function, jump to the right bucket, and then if necessary search that bucket for the right entry. So a whole slew of different ways that we might wind up implementing our symbol tables. Again, which approach we're going to take is going to be based on how big we expect the symbol tables to get, right? How long we expect it to take to be able to search these things. All right, the one other thing I wanted to mention was the idea of nested scopes and our symbol tables. We've kind of touched on this a little bit in the labs. We suggested the idea of coming up with some kind of unique identifier for each scope. And so for each item that's declared, you say, okay, well, in addition to recording the information about it, we'll record which scope it's in. So we'd have a variable x in scope 17 and a variable x in scope 3 and a variable x in scope whatever, and they're each different variable x's. And if we were going to do something like that, then maybe we maintain a stack or a list of active scopes. And when I see a reference to an x, I go through my stack of scopes and check the top scope and see if it's got a reference to x, and if not, I check the next one down, and if not, I check the next one down, and we work through an approach like this. Another approach is to actually generate a new symbol table for each scope. So each scope has an entire symbol table that's just the stuff that's in that scope. And so now when I want to go through and search something, then I'd have, again, either a stack or a linked list of these active symbol tables. And I search the most recent one first, and if the thing I want isn't there, I search the one before it, and if it wasn't there, I search the one before it. Similar sort of idea, just a different implementation. And so there are all kinds of different approaches we can take to the implementation of our symbol tables, and just think about the impact that's going to have on the complexity of our implementation versus the speed up it potentially can give us when we're actually trying to use these things. All right, I think those were the key points I wanted to bring up for our intermediate representations for now, or internal representations for now, and we'll start looking at some more fun and exciting ideas next time around.